Welcome to Calculus. In this chapter, we're going to be reviewing a number of concepts from pre-calculus or algebra that we'll need from time to time as we go through our calculus ideas. But because this is a review in this chapter, we're going to blast through this material rather quickly. In this section, we're going to be talking about some graphing concepts. Let's begin with the notion of graphing by point plotting. It's the most fundamental way of constructing a graph. Point plotting is the matter of making a table of values, and this is really a table of x, y values that are solutions points to the equation. And if we want to make our table of values, you may recall that the way you do that is that you take a value of x or y, plug it into the equation and solve for the other variable. Here, if we're taking a value of x to be 3, we pop it into the equation. If 3 is squared, we get 9. 9 minus 3 is 6. So when x is 3, y is 6. And in that way, the entire table can be constructed. So we have a number of points to plot. We come over to our coordinate plane. We plot those points. You can see the points as the dots on the graph here. I've also constructed the graph by creating a smooth curve through the points. That's the whole idea with the point plotting method. Now, the downfall of the point plotting method is that as graphs become more and more curvy, you need more and more points to plot. And here we've just plotted a few points, and yes, we know how this parabolic curve behaves, but if we had a polynomial function, you see, that had lots and lots of curves, we certainly wouldn't be able to tell with just this many points. We would need maybe 40 points or something like that. Well, it takes about maybe 10 minutes to construct the graph of a parabola like this, plotting about 7 points. But the graphing calculator can plot 95 points in about 10 seconds. You see, so the graphing calculator will play a big role as we examine graphs from time to time. And you've seen that before, I'm sure. Now, another idea related to graphing is the notion of intercepts. Intercepts can help us with the graphing process. It also helps us in other areas like finding solutions to equations and such things as that. But there's the graphical idea, or a graphical approach to the notion of intercepts, is also an algebraic approach to the notion of intercepts. The graphical idea, if we're able to look at a graph and identify intercepts, then the way we do it is we say, well, what's an intercept? Well, an x-intercept is the position on the x-axis where the graph crosses. The y-intercept, no surprise, is the position on the y-axis where the graph crosses. So all we're doing is looking for those points. If we come back over here for this graph, for example, and try to identify intercepts, if we're looking for a y-intercept, the place where the graph crosses the y-axis, it's pretty easy to identify. It's at this point at 0, -3. Now, a lot of times the intercepts can be identified in a couple of ways. It's acceptable to say that the y-intercept is at -3. And you're understanding that we're on the y-axis and we're identifying the position on that number line as -3. So here we are. Another way is to identify it by using coordinates, and the coordinates of the point would be 0, -3. So two ways of identifying intercepts. The x-intercepts are at, well, let's see, there's one here, one here. This one is about 1 and, let's see, 1 and 8/10, 1 and 9/10, let's say 1 and 8, 1.85, something like that. And I'm stammering around here because this is the downfall of identifying intercepts using a graphical method, or just kind of looking for the intercepts. Here we are at -1.85, let's say, or something like that. So we're having to estimate if the value is not an integer value. And that brings us to the algebraic approach. To find intercepts algebraically, we use sort of the concept, the big picture of the notion of intercept. And incidentally, the big picture idea, the concept idea, that's the way we're going to approach many, many topics throughout calculus. And certainly here with algebra, I want you to recall your algebra experience by thinking in terms of the big picture. If you don't understand something, go back to the very basic idea for that topic. And here the very basic idea of intercept is the position where the graph crosses one of the axes. Now, that jump starts a logic pattern for figuring out algebraically how to do that. You see, if we have a graph, and let's say the graph is not here, we just have a coordinate plane, and the graph crosses the x-axis somewhere, whether it's here or here or here or here, we just don't know. But the prevailing characteristic about all of these points is that the y component for every point on the x-axis is 0. The y component is 0 for our x-intercept. In a similar way, the x component for any point on the y-axis is going to be 0. That is, this point is 0 and something. This point is 0 and something. And that idea of having the first component being 0 for every point on the y-axis gives us an idea of how we find the y-intercept algebraically. We simply let x be 0. For the x-intercept, we simply let y be 0. So if we're finding the intercepts for, let's say y equals 2x minus 3, then to find the x-intercept, let's see, x-intercept, the y component is 0, so we'll let y become 0 in this equation. Replace y with 0, we have this. We're solving for x, we find x to be 3 over 2, so the x-intercept is 3 over 2, or 1 1/2. The coordinate version is 3 over 2, 0. For the y-intercept, same idea. The place on the y-axis where the graph crosses, the x component will be 0, and therefore we take the equation, replace x with 0, and solve for y. We find y to be negative 3. The y-intercept is negative 3, or the coordinates 0, negative 3. Doesn't make any difference how complicated the equation is. The concept is the same. If the equation looks like this and we're looking for intercepts, then we just pop values into this equation. Now, we're reviewing several ideas here. It's not just intercept that we're reviewing. We're going to do a little manipulation here. If we're looking for x-intercept, the place where the graph crosses the x-axis, the y component is 0, so we just replace y with 0 in this equation and solve for x. Now, we're solving this for x. All right, so here's the next challenge. How do we do that? Well, there are a couple of ways of very quickly getting into this problem. One way is to see a fraction over here and make this a fraction by thinking of it as 0 over 1 and cross multiply. Now that's a way of getting us out of the fraction notion. And doing that, we'd be multiplying this times 0, giving us 0, and 1 times the right numerator would give x squared plus 3x. Another way, even more conceptually than the first, is that if a fraction is going to be 0, and you see that's what we have here. We have 0 equals this fraction, or this fraction is equal to 0. For a fraction to be equal to 0, the numerator of the fraction has to become 0. And actually the denominator has to become non-zero. When the denominators of fractions become 0, we have an undefined situation. So we're really looking for the value of x that will cause the numerator to become 0 here. And we hope that that value does not make the denominator 0. All right, so we could just say, well, for this to be true, the numerator has to be equal to 0. So it's another way to quickly get into the problem. Now we see a quadratic situation, expression on the right. We'll solve by factoring. We take out the common factor x. We ask ourselves what value of x will make each factor 0. This factor is 0 when x is 0. This factor is 0 when x is negative 3. So these then are the values of x that will cause the numerator to become 0. Neither of them will cause the denominator to be 0. They are indeed solutions to the equation. So what are the x-intercepts? You see, and the x-intercepts are at these values, and the coordinates of x-intercepts are 0, 0, and negative 3, 0. For the y-intercept, it's much easier in this problem. We're replacing x with 0, and there are a lot of x's to replace with 0. We take all of these x's, replace with 0, we have this, and then when the smoke clears, we find y to be 0 over 1 or 0. So the y-intercept is at the origin, 0, 0. Another idea related to graphing is the notion of symmetry. Symmetry is the idea that an object, a thing, in this case a graph, kind of looks the same left and right or up and down, sort of. Trees have this symmetric quality. If you think of an imaginary line right down the middle of a tree, a vertical line down the middle of a tree, it kind of looks the same left and right. Well, with graphs, if we're talking about symmetry with respect to the y-axis, then the graph looks the same sort of on the right as on the left. The right and left are sort of mirror images of one another. We have three kinds of symmetries that we're looking for and examining for. We're going to look at them just visually or graphically, and then we're going to talk about them algebraically. Visually now, symmetry with respect to the y-axis has this same looking quality on left and right of the y-axis. Another way to think about it is like this, and I like to think of it as a situation where if you had this on a piece of paper and you folded right down the y-axis and you folded the graph on top of itself, it would imprint on top of itself. So if you fold this way or this way, then the graph imprints on itself. Symmetry with respect to the x-axis, it's the same idea. Think about the folding notion. If we fold along the x-axis, when we fold the graph down this way, that this part of the graph imprints on that part of the graph. Or if we fold up, it would be the same idea. Here's another kind of symmetry. The third kind of symmetry is symmetry with respect to the origin. And a way of looking at it is as a double fold. You see, the double fold idea, if we fold along this axis and then fold along that axis, then this part will imprint on that part. You see, when we fold down here, the graph comes down here. When we fold over here, it comes over to this position. Now let's talk about an algebraic approach. We can kind of understand what needs to happen for an algebraic evaluation of whether or not we have any of these kinds of symmetry by just looking at some points. If we take a point over on this side of our graph that is symmetric to the y-axis, just take any old xy point, then it turns out that if xy is on the graph, then also when we fold over we can see that negative xy is on the graph. And that gives us a way of evaluating the situation. Incidentally, we could have started with an xy right here. We could have said, well, here's our xy. It doesn't make any difference whether x is negative or positive or y is negative or positive. We're just calling it an xy. We're not identifying them as being positive or negative here, but we do know this, that if xy is on the graph, when we fold over that way, then what we have is the negative of x, the opposite of x, and y that's on the graph. You see, so the idea prevails regardless of where we are on our graph or which point we select first. Well, this gives us an idea of how to test for this kind of symmetry. If it is the case in an equation that you can replace x with negative x and have the same equation that you started with, manipulate to the same equation you started with, then you have symmetry about the y-axis. In a similar way, if we're talking about symmetry about the x-axis, notice that here's what happens to points when we do this folding idea. A point xy, when we fold down, becomes the point x negative y. And this trip starts the idea of how to test for symmetry about the x-axis. Replace y with negative y, we should get an equivalent equation. And let's go through the process. I'll get to the symmetry about the origin in just a minute. But let's test these algebraically. If we're talking about testing this equation y equals x squared plus 3 for symmetry about the y-axis and x-axis, here's what we do. You take the equation and to test for symmetry about the y-axis, replace x with negative x. So this x becomes negative x. Now notice it's negative x, it's squared. So negative x times negative x, oh that's x. You see squared. So we have x squared plus 3, the same equation that we started with. So we've manipulated it back into the original equation. Therefore, yes, we do have symmetry about the y-axis. And we kind of knew that from before. You probably recognize this pretty easily as it's a quadratic equation. It's a parabolic curve that's just adjusted 3 units up on the coordinate plane. It opens up like this, and the vertex is 3 units up from the origin. Okay, no big deal. So it was a predictable kind of thing that it's symmetric about the y-axis. It's not going to be symmetric about the x-axis or about the origin, but let's test it anyway. All right, so to test for symmetry about the x-axis, because of this idea of folding, we know that we replace y with negative y and evaluate. Well, the y is replaced with negative y, and then we go about evaluating. No matter how we manipulate it, we can't get it manipulated back in the original form. If I've multiplied through here by negative 1, and we have y equals negative x squared minus 3, well, that's not the same as what we started with, so no, we don't have that kind of symmetry. Now, concerning the symmetry about the origin, if you recall, it's kind of a double replacement idea. It is that if we do this fold down here, we're sort of replacing a y with negative y. The x's remain the same, y with negative y. And when we fold over this way, we're replacing an x with a negative x. So the idea is that we have symmetry about the origin if we can take our original equation and replace every x with negative x and every y with negative y and get an equation equivalent to the one that we began with. So we would take the x's and y's and replace them. Now over here what we're doing is taking this y, replacing with negative y, take the x, replace with negative x, and it looks like this. And then resolving this is x squared, so we have x squared plus 3, and there's no way to change this back into that. You see, manipulated back into that, so no, we don't have symmetry about the origin. Another way, incidentally, to look at the symmetry about the origin is that it's really a 180-degree twist. I mean, think about, we could leave this alone and twist this, just twist it 180 degrees using this as a pivot point, twist it right here and it twists right on top of itself. Another way to look at it is just twist the whole thing, you see, and it imprints on top of itself. And the others could be thought of as a twist as well, because if we twist around the x-axis here, you see, twist the whole thing and it just flip-flops back on top of itself. Twist this rascal, the symmetry about the y-axis to test, twist it about the y-axis, and bam, we have this. So it's a 180-degree twist no matter how you cook it up. Let's talk about finding points of intersection. Now in algebra, this was the matter of solving systems of equations. If we have this equation and we want to solve them simultaneously, we had graphical methods of doing this, and we also had algebraic methods. We're going to look at both. Finding points of intersection is the graphical way of solving this system of equations. You might recognize this as the equation of a circle whose center is at the origin and whose radius is 5, and this is the equation for a straight line. So we're just looking where the line crosses the circle, the points of intersection for those. And graphically, it's a rather simple matter. If we're talking about a circle whose center is at the origin and whose radius is 5, then we're talking about this circle graphically. And then using the point plotting method that we talked about earlier, we could plot points and solve or construct the graph of the line. Now we're looking for points of intersection, so we just look where the two graphs cross, and the graphs cross at this point and at this point. This is the point 3, 4, and this is the point 5, 0. Now those points of intersection, though, are there's kind of like more to it than just points of intersection. The most important relationship between graphs and their related equations or functions is that every point on a graph has associated with it coordinates. And the coordinates of a point on a graph are values of x and y that solve the related equation. Every point on this circle has some coordinates associated with it. And that xy pair for those coordinates will solve the equation related to it. Same way with the line. Every point on the line has coordinates associated with it, and the coordinates of those points will solve the equation for the line. So truly, the graph is a picture of the entire solution set for each of those equations. So you take an equation, you got a picture of the solution set. Take the other equation, draw a picture of the solution set. Now, what are we identifying when we identify the points of intersection? We're identifying the common solutions for the two. This is a point, since it's on both graphs, it's a solution point for both equations. So this is a solution of both equations, and that too is a solution of both equations. And this is just a way of conceptually thinking about that relationship between graphs and equations. Let's look at the algebraic way. If we're solving this system algebraically, you may recall that we basically had two methods, two ways to solve simultaneous equations. There are others, but two fundamental ways. One way was by the addition method, where you set up a condition where you add the two equations. Another method is called substitution, and this particular system lends itself well to substitution. So the substitution way method works like this. You take either equation and solve for any variable. Now here it's pretty easy to solve for y. I'm going to label this equation 1 and this one equation 2 just for organizational purposes. In equation 2, if I solve for y, I'll subtract 2x on both sides and get this. Now, when we solve one equation for one unknown, we take that information and pop it into the other equation. So here we have one equation solved for one variable. We'll take the other equation, equation 1, and in place of the y, you see we solved this for y. So in place of that y, we're going to put this value for it. We're substituting this value of y from the first equation into the second equation. So instead of y squared, we have this expression squared in the other equation. That's the whole idea. That's the concept or the general idea of solving by substitution. Now, let's see, expanding here, squaring this binomial, we get 4x squared minus 40x plus 100. Then subtracting 25 on both sides will kick this 25 out of the right side. So we get this. We want all the terms on one side. I'm anticipating a quadratic equation, which is what we have here. So now we collect like terms. We get 5x squared minus 40x plus 75 equals 0. Factoring, we get 5 times x minus 5 times x minus 3. The value of x, it will cause each factor to become 0. This factor becomes 0 when x is 5. This factor becomes 0 when x is 3. Now, we're not finished once we get here. We're finding only the x components, you see, for our solutions. Our solutions are really an xy pair. And here's the x component for one of them. Here's the x component for the other. We take this information, this x equals 5, and we put the information, come back up here, we put the information back into either of those equations. If we replace x with 5 in this equation, the second equation, which is a little easier, then this becomes 5. 2 times 5 is 10. Subtract 10 on both sides, we find y equals 0. So that's why when x is 5, y is 0. So the point 5, 0 is one of the solution points, as we found earlier. For the other, x equals 3. You come back up here, you replace x with 3. 2 times 3 is 6. Subtract 6 on both sides to find y is 4. So when x is 3, y is 4, and the point 3, 4 is the other solution point. So that's the whole idea of solving this system algebraically. Now, let's talk about another idea. The idea is modeling. Modeling is one of the most important ideas in all of mathematics. It's kind of like, it's why we do mathematics. Modeling is the business of creating or finding an equation that will allow us to solve a certain problem. Now, the mathematical model, the equation, is occasionally built into the type of problem that is before us. If we're talking about distance, rate, and time, then we use the distance formula. If we're talking about the perimeter of a rectangle, we use the P is equal to 2L plus 2W formula. So a formula often acts as a mathematical model. Other times, however, we have to make up our own model, and sometimes that model can come from the structure of the problem itself. It's a kind of a word interpretation kind of situation. Okay, fine. But the most intriguing, the most interesting situations involving mathematical modeling is where you have information, you have data, and you take the information, that data, and you build a model from the data. Now, here's what I mean. Suppose we have information about a year associated with the acreage on a farm. The average acreage of a farm in 1950 was 213. In 1960, the acreage increased to 297 acres per farm. In 1970, 374, and so on, and all the way down to 1994 when the average acreage was 478. Notice it's increasing as the years go by. Well, it's possible for us to build a mathematical model, build an equation that will relate these two variables. And that's the whole idea of this kind of mathematical modeling. Now, and once we have built the equation based upon these two variables, the variable of time and acreage, then we presumably will be able to determine what the average acreage will be in some future year, like in the year 2020. Or we might be able to predict in what year will the average acreage be, say 600 acres per farm, something like that. So we have a relationship between the two variables. And it's not absolutely accurate. It won't be absolutely accurate. It's only a way of estimating something in the future for us. Well, let's talk about how this modeling takes place. Here we have, you see, we have information involving two ideas, years and acreage. And this becomes an ordered pair, an XY pair. Those points can be plotted, therefore. And the plot is called a scatter plot. When you take information like this and you put onto a graph, you have a scatter plot. And the scatter plot will often appear in some kind of pattern. Now, sometimes there's no pattern at all, so we can't make a mathematical model. But a lot of times there will be a pattern. Now, this particular scatter plot has a sort of a linear pattern, you see. So we would be looking for a mathematical model that is a linear equation that emulates this. Now, when I say emulates it, we're looking for the equation that will give us a graph that fits the data best. And a best fitting graph would be a graph that goes through the data points kind of like this. Kind of like goes right through the middle. There are just as many points above as below, and they're just as distant above and below. Something like that would be a good linear model. Okay, this other model, this other scatter plot is more of a quadratic type of arrangement because it's beginning to curve here. So a quadratic model would fit this data better than a linear model would. And it turns out that the calculators, graphing calculators, have a tremendous ability at being able to give us a certain kind of model, certain kind of equation that emulates data like this. Oh, and incidentally, when we were talking about the points of intersection, I failed to mention the use of the calculator at that point as well, but certainly we could construct the graphs of our two equations and trace along the graphs and find those common points of intersection. Again, the use of the graphing calculator. All right, back to this problem. In graphing calculators, there are many more models than just linear and quadratic. There are exponential models and logarithmic models and logistics models and so forth. Lots of them. And so we could choose to evaluate a pattern using any of those models. And the calculator will tell us when it goes through a process called regression, will give us a correlation between the model and the data. You see, and the correlation that we're looking for is one that's very close to 1 or -1 in some cases. So we have a number of models to choose from, and we choose the one that has the highest correlation coefficient, and that's the one that we would use on the problem that we would have at hand. Well, I'm talking about an awful lot of different things here. Let me organize the information like this. Here's what you go through when you go through this notion of mathematical modeling. You have data, you have information. All right, then you create a graph. You see, you put that information onto the graphing calculator, and you create a scatter plot. And you've probably done this before in algebra, and I hope this is just a review for you, but you create your scatter plot, and then you choose some kind of model. You go into another area of the calculator, and you're going to do a regression analysis. And so you would choose a model. Now, sometimes you won't know what model exactly to choose. You might look at the scatter plot, and it fits a certain model, and you say, that's the one I need. So I'll make that model. Well, other times you might say, I'm not sure which one works best here. Maybe it's quadratic, maybe it's logarithmic, I just don't know, something like that. And so you'll say, well, let me test both of them. Let me see which one gives me the best fit. So you would choose whatever models you want to, then you would compute the regression using those models, and then you would notice some correlation coefficient. And you're looking for one that is nearest 1, presumably. Sometimes -1, as I said before. But one of them might have a correlation of 0.85, and another would have a correlation of 0.92. Well, you would choose the model that has the correlation of 0.92. It's just a better fit. And so you're selecting an equation. Now when you select an equation, what the calculator is giving you is information about coefficients and a constant that would appear in that particular model. For example, if we're talking about a linear model, the linear model I think is in the form ax plus b or a plus bx, pretty interchangeable. But at any rate, you're getting the value of a and b, you see, in either one of those models. And you recognize that, I think, as being the slope-intercept form for a linear equation. For the quadratic model, you're talking about a model which is in the form ax squared plus bx plus c. That's the general form of a quadratic. You see, and the calculator in this regression analysis is identifying the value of a, b, and c for you to put into this model. And you can actually, on the calculator, you can actually overlay the model that you've chosen, you see, with the scatter plot to see how good your fit is. And then you can trace along your graph, if you want to, the graph that you just created, and you can go to some future date and find out when that acreage is going to turn out to be 600 acres per farm in the United States. Find out what year that's going to be. Be an easy task. We're going to run through the modeling process on the calculator now. Notice I'm using the TI-83 graphing calculator. From time to time we'll be using the TI-83 and the TI-86 graphing calculators. Well, to start this problem, and we're talking about the problem involving the years and the acreage, the farm acreage, we'll press the button marked Stat, and this is the menu that shows up. We want the first item at the top of the menu marked Edit. We can either press number 1 or press Enter at this point, and it allows us then to enter information into various lists. Now we'll enter the year information in L1, we'll enter the acreage in L2. And for L1 then we start at 1950. We can either enter this as 1950 or we can start with 50 just to make the items that we enter a little bit simpler. We could even start at 0. We could say, let's let 1950 be 0. In fact, you know, that might be the easiest way for us to go here. Let's put 0 for 1950. Then 1960, you see, would be 10 because it's 10 years after 1950. And then 20 would be for 1970. And then 30 and so on. 40. Now, the 40 corresponds to 1990. We also had a 1994, which would correspond to 44. And I'll press Enter here. So those are the years. Now, notice we're using as our benchmark year the year 1950, and it corresponds with 0. It's just a way to do things. We could input these as 1950, 1960, 1970, and so on, or we could make a basis year, and usually that's a handy way to approach the situation, is have a basis year when our information starts and then work from that point. That's why I'm setting it up this way. All right, the acreage here, 213 for the 1950, and then 297. I'll just input these as quickly as I can. 374. 426 was the next one. 461. And 478 was the last one. All right, now we'd like to look at a scatter plot. And I'm going to go to a main screen here and explain to you the scatter plot is in this stat plot menu. And it's the second function on y equals. So I'm pressing second y equals for stat plot. And all this allows me to do is turn a plot on. Now I can cursor from one plot to the next, but I think what I'll do is I'll just turn this plot on by pressing Enter here. And now I have a number of options. I want the on option, so I'm pressing Enter. And there are other options here. The type, for example, the first item, the default item is for scatter plot, and these are for some other items in statistics. And we don't need those, so I'm not selecting them. It is this top or first item that we want. The others are also on the default settings that we are looking for. Here, the X list is in L1, that is our X value, the first component, the first coordinate of the items we want to plot is in list 1. The Y list is list 2. And the mark that we're going to make on the graph looks like this. It's going to be a little square as opposed to a little plus sign or a little dot. So all the rest of the items are on default settings. All right, I'm almost ready to go. I need to set up the window though to accommodate the numbers that are involved here. And remember that the lowest x value we had was 0, so to give ourselves a little room, I'll leave the x minimum at -10. The highest x value we listed was 44, so I'll make, let's say 50 as the x max. Now our smallest y was 213, and really the situation here is rather arbitrary. I could set the y value as 0, I could set it as 200 if I'm at 213 for the smallest value. Let me make it 100 here, and as I say, it's arbitrary. There are a lot of right ways to do this. Y maximum, the largest y we talked about was 478. I'll make the max 500, and here is the graph. Well, now notice that, that this value, the value right here at 0, is almost undiscernible, but that is part of our graph and or part of our scatter plot. So we have to take it into consideration. Now, the reason for performing the scatter plot is to look at the pattern that is displayed here. And it's not quite a linear pattern here. We could try a linear regression if we wanted to, but the linear regression, the line, will not be able to contain all of these points. We might think, because of the pattern that we have here, that we kind of have a curvature like this. I'm exaggerating a little bit here, but that curvature would lead us to believe that maybe a quadratic pattern would be better, or a quadratic regression would emulate this graph, this scatter plot, a little more closely. Well, because of the pattern that we see, then, we want to go through and try to perform that regression, a quadratic regression. And incidentally, before we go to that, let me just show you something here. Notice that we're really close to the top of our graph here with this particular point. We're close to the right side. We can just arbitrarily or very quickly go back to the window settings and make some higher window settings in order to accommodate that situation, in order to see a little bit more. I might make this maximum 75, and I might just slide down here and make the y maximum, let's say 600, and then look at it right quick. So it's really okay to just fool around with this a little bit and jump back and forth and just make what you see convenient to the eye and pleasant to deal with. All right, at any rate, let's go through the regression situation. We go back to stat. Now I'm pressing stat, and we want to perform a calculation, so I'll press the right arrow button. And now we want to slide down and notice the various regressions. The items at the top we're not interested in right now. But this item, item number 4, is a linear regression in the form ax plus b. Here we have a quadratic regression, which we'll come back to in a moment. Cubic regression, quartic regression, that's a 4th degree polynomial function for that one. Another linear regression in the form a plus bx. Here's a natural log regression. Here's an exponential regression. You see there are lots of regression equations here, a power regression, logistics, and so on. So there are a lot of items to choose from as we get a little more complicated with the scatter plot, and we are able to make better decisions about the kind of pattern that we're looking for. At any rate, we're going to select number 5 here, the quadratic regression. We'll press enter, and then enter again, and the calculator will make the calculation of the quadratic regression. Now notice that in this regression model, the equation is in the form of ax squared plus bx plus c, and the regression analysis is giving us the value of a, b, and c. It also gives us a value of r squared. Now this is an item that I selected for the calculator to compute for us. This is called a coefficient of determination. There are other coefficients or items that the calculator will calculate. One item is called a correlation coefficient. This is very similar. Coefficient of determination. It gives the relative effectiveness with which this regression equation is going to fit the data. And as this number is very, very close to 1, our fit is extremely good here with this information. If this was like 0.85, then the fit would not be particularly good. But this just tells us how good a fit that we have. Incidentally, let me show you how to select the r squared on your calculator. There's a second function marked catalog on the display at the bottom of the calculator. It's the second function on 0. Now I'm going to press that here just to show you what it looks like, but it catalogs a lot of items and functions that are on the calculator. And I'm going to cursor down. I'm just leaving the cursor depressed here, and here's what I selected. This is diagnostic on, diagnostic off. I could turn off the idea of the calculation for correlation coefficients and a coefficient of determination, which we have here, or I can turn it on. I had turned it on before. All right, let me leave this area then. Just wanted to show you that. It's kind of an advanced situation for us. But at any rate, here's our quadratic regression, and we can now take the A, B, and C and copy them down onto a piece of paper if we want to, in order to enter this information into our equation where we're going to construct a graph. And we would do that by pressing y equals and then listing the, writing the equation as ax squared plus bx plus c using the a, b, and c that we just calculated. There's another much easier way to select the regression equation. The calculator is able to select this automatically, and we select that in a menu. Now, I might need to poke around here. You're not going to remember every protocol that I tell you about, that is every button sequence. You might have to poke around a little bit to find these things. I'm pressing VARS here, and the item that I want is number 5, so I can either press number 5 or cursor down to it and press enter, which I'm doing here. And now there are a number of selections at the top, and the selection I want is an equation, and it's the top equation that I want, the regression equation, and I'll press enter, and now notice that the equation is entered automatically for me. All right, let's take a look at the graph then. I'll just press graph, and now the graph of the regression equation is right on top of the scatter plot. Now that allows me to notice how well the regression equation is fitting the information, and it fits extremely well. It looks like it goes through every one of those points. And this also allows me to answer some questions that I might have about the information that was given. It allows me, for example, to answer the question about, gee, what will the average acreage be in a particular year? Now, pressing trace, I have an icon, it's blinking. I'm pressing the right arrow button, and notice that I'm jumping from one item on the scatter plot to another. And we can verify the coordinates here if we want to with our list or with the information that was in the table from before. If I press the up or down arrow key, I jump to the graph. Now, do understand that an x of 30 means we are 30 years from our basis year. Our basis year was 1950. So this really corresponds to the acreage in 1980. And it's important to just take note of that, or just understand that as we go along. All right, I press the down arrow button. Now we're on the equation, or excuse me, the regression equation, or the graph of the regression equation. And I can slide over to the year 2000. Now, if our basis year of 0 is 1950, then the year 2000 would be 50, because it's 50 years from 1950, you see. So I can go over, whoops, I overshot it here. Here we go. At 50 and a half years approximately from our basis year, which is in the year 2000, we have an average acreage of 487.87, or 488 acres as the average acreage on a farm. So that's one thing, that's the kind of thing that we can do. We can do some forecasting. We can forecast a little further out, as far out as we'd like to go. Now, I'm noticing that we have a sort of a top on the graph here, so we could actually cursor over to a point that we perceive to be the very top point. Now, I'm going to back up a little bit. I want the highest y value. Look at the y values change as I cursor over to the right. You see they're getting a little bit bigger, a little bit bigger. I want the biggest one I can find. I've got 492.7, 493, 493.3, 493.38. We regressed there. We went down a little bit. Well, this looks like the biggest number that I can land on at the moment on this graph. So I'm thinking that in order to forecast a
peak for the average acres on farms in the United States it will happen 58 years from the basis year, or in the year 2008 approximately, almost the year 2009 because of this. But at any rate, this is the great value of a regression equation that fits a particular model for data.